This is a test project about making T-nuts. These are T-nuts. Fairly simple milling operation. Requires planing, milling, sizing, drilling, and tapping. So I thought I'd make a video about this. T-nuts are used on my milling table to slide into the T-slots and allow me to secure pieces to the table for other milling operations. Didn't have enough, so I decided to make a set of at least 4. So here's how we do it. I had some cold rolled steel, which was 1 inch in diameter, and I decided I would make it out of that. So I put it on the milling table, secured it in place, and used milling cutters. Particularly these were some Chinese import cutters that I was using, milling bits that I wanted to test out. So after securing them, the idea is to mill a flat on either side of this bar, which would be the width of the slot, minus a few for clearance. So you set the milling bit against the bar, touch off. As you see, I make a couple of minor chips. Set the RPM speed. Now it looks like it's going backwards, but that's a camera issue. And so after we've touched off, found the right milling speed, which I looked up in a little manual, we then proceed to mill a flat on each of the faces. So I'm going to start off by milling this by manual drive. I'm turning the X drive by hand until I determine that the cutting speed is just about the right running rate. And so at some point along this way I said, it looks about right. So I'm going to turn on the X feed, which is an automatic drive, and that gives my hands freedom to do other things, but it also allows the cut to proceed as smoothly as possible. So right here I've changed over to the automatic drive, and it's going to allow me to be able to do other things. For instance, I've determined that this device, which I will show you later, is in the way. So let's take it off, and while the thing is cutting, I can proceed to do other things as long as I don't step away from the machine while it's working. So I'll mill 1 pass, set it down, mill a 2nd pass, and so on, until I've removed the amount of material necessary on this side. I've made a drawing. I calculated out how much would give me the proper amount of clearance for this project. So here's the first pass, and there'll be several passes at this cutting speed in order to be able to accomplish the task. So we'll make several passes on this side until we get down to the right dimension. And once to the right dimension, and we're going to take the piece out and turn it over. You can see here another view of the setup. I have on the green box on the far left side is the power feed, which I'm now using in a fast motion just simply to clear the cutter from the work material. I've turned off the drive. By opening the door, it's the same as hitting the stop switch. Both accomplish the same thing. It's a perfectly safe way to do it. So I'm removing the piece from the milling vise, turning it over to the other side. Now I have a flat, which I can set against my parallels. You can see me adjusting them right here. The parallels are very precisely milled pieces of metal designed to hold projects at a certain height in the milling machine. So I've now reversed it, put the cut side down, tightened the vise, and now I can mill the same amount of material from this side as I did on the first side. Close the safety door, restart my cutter, and mill the second side. Same operation as the first. Set the depth properly, and I'm going to use a little fast forward on here simply to get us through some of these cuts a little bit more rapidly. I'm not really cutting this fast, it's a little too much, but you get the idea of what the process is like. I'm doing exactly the same thing on this side of the piece of cold rolled as I did on the first side. So we'll proceed to get this side flat through a number of cuts. Once both sides have been flattened, I put a little dichem, which is a blue marking solution, on one side of the billet. I've set my calipers at 700 thousandths, 7/10 of an inch, and I've determined that's the length or height of the piece that I'm going to need. So I'm going to scribe it, and all that does is mark through the dichem and give me something that I can take to the bandsaw. Now, the bandsaw that I have is a modified wood bandsaw. You can see a larger cutting wheel in the back, driving wheel that is. I put a 3 horsepower motor into it, variable speed drive, and an RPM indicator that gives me feet per second or feet per minute cutting speed, so I can set it for steel, aluminum, and so on. And this is set for cutting steel. Again, not at this pace. I'm going about 4 times cutting speed right here. It's a tedious, slow process, and you see me mark it off, push it through, and I'm going to make several pieces. I need 4. I'm going to make 6 in case I have any loss due to lapses of memory or machine failure, so on. And for the last piece, I'm going to grab a piece of wood off the floor and use it as a push stick. Better hold on it. Plus, the billet itself is beginning to get a little bit warm and hard to hold on to. So there I've cut 6 pieces with a little leftover material that I might be able to use later. After you cut down the pieces, one of the things you always have to do after every cutting operation is remove the burrs and file the edges down with steel or aluminum. Those edges will interfere with taking accurate measurements or holding people accurately. So now I've set the piece back on a set of parallels, and I've used a square to make sure that the edge is perfectly vertical. And my job here is to slowly eat away on one side of the piece so that it is exactly perpendicular to the edge. And now I have 2 reference surfaces, one flat and one on the edge. And you can see I'm creeping up on it just little by little, taking off the least amount of material but making sure that the whole face is dead flat to that edge. Now once that's been done, I've got all 6 pieces. I'm going to put I'm going to take a measurement on it first to be sure that I've got a knowledge of how thick this piece is. I know it's oversized. And I have marked in dichem on the face exactly the height this piece needs to be. And so for this first one, I'm going to proceed to cut it very slowly, little by little, until I come down to the pencil mark on the face. And you can see how the burrs roll off the side and how they would interfere with taking accurate measurements unless they are removed prior to doing that measurement. So I'm just taking a series of cuts, little by little, until I can get this piece down. Now I'm trying to be sure that I am not doing what's called a climb cut. That means I want the bit rotating in the reverse direction to the feed. Safer that way. Well, I've got that piece to dimension. Take it out, check it, and now that the cutter is already placed down at the right dimension, all I have to do is to cut across each of the remaining pieces, and they will now all be of exactly the same thickness. And as you can see, I was careful to allow enough extra material when I bandsawed these pieces to allow them to be planed, it's a planing cut, down to the dimension I need. So I have to go through all 6 pieces this way. You get pretty good at it after a while, even though it is at 4 times speed. The cutter I'm using is a import one, as I said earlier. It seems to cut pretty well using the side cutting capability for which it was designed. The end cutting wasn't quite as good as I would have liked. You'll see later in this video I have changed to a different cutter for doing more cuts. So 1, 2, 3, 4, 5, 6 pieces. And we'll get through all these things pretty quickly here. parallels that they're setting on are precisely machined to various different widths. I have a set of parallels of all different dimensions, allowing me to raise pieces to different heights. Well, guess where I am back here now. They've all been cut to the same height, the widths are right, and now I'm down there taking the daggone burrs off all over again. Just got to deburr 6 different pieces. I'm using a fine milling file, that's what I was trying to say. I'm not going to go back and re-edit the audio on this, it's not worth the trouble. But every face and every edge needs to be completely cleaned of all those burrs, and steel requires a little more time than does aluminum. Now here's a trick. The piece is put back in, and I have a scale set next to the edge, and I have a 1/4-inch drill bit loaded into the drill chuck, and they are clamped against each other. And as I move the table forward and back, you'll notice the scale begins to rotate a little bit. Once it's perfectly vertical, I know the center of that drill bit is on the center of that 1-inch round edge, and I can calculate 2 different dimensions at the same time. So this is going to allow me to find the dead center of this piece. I measured the drill bit, and I know it actually is, in this case, a 1/4 of an inch. That's 250 thousandths. I need to find the center of the drill bit. That would be half of that distance, 125 thousandths. And I need to also remove the thickness of that scale I put in there, which I have measured to being about 3 thousandths, 33 tenths. So altogether, I need to move over to the left 128 thousandths of an inch to find the edge of the piece. Well, the easiest way to do that is to go over here to my digital readout, which I haven't used at all. And as you can see, it has an X and a Y scale. It measures out to the 100 thousandths of an inch, which I can't do anyway. So let's turn it on, set it up. Now I'm going to zero the Y-axis because I have found the Y direction by using that little ruler technique. Now to find the axis the other direction, I need to overset to the left. I zeroed it so I can go over to my 125 thousandths plus another 3, which will take me to the edge of the piece. There's my 128 thousandths. Now, I'm zeroing it because it's easier than adding numbers in my head. So I'm at the edge of a 1-inch diameter piece. And for me to get to the center, I've got to go a 1/2 inch over. And this gives me a center on the Y-axis and a center on the X-axis. So now I have where that piece is clamped on the milling vise, exactly located the dead center of the piece in both the X and the Y plane. So the digital readouts are very handy for tacks like this. There are other ways to do it, but this is the way I've chose to do it. Now, because I'm going to take out the pieces and put them back in, I want them all to have the same dead center location. So I'm reinstalling my device that is used simply to detect and center the edge of the piece left and right. So I put it back in. It's a homemade version. There are other commercial ones on the market. And I've locked it down to the milling table. I raised it and lowered it so when I start making cuts and drilling holes and such, I'm not going to run into it. I've extended the bar out to just touching the edge of the piece, which means when I take it out, put the next one back in, touch the bar, it will be back in exactly the same location. So nice and tight, nice and secure. So now what I can do is do the drilling and tapping operation. I'm doing that because I've got the right chuck in the place already. So I've installed the drill bit necessary for drilling the hole that will eventually be tapped, and tapped for 3/16 or 5/16 threads. I'm using a little tap magic. I want to keep these drill bits and these taps for as long as possible. So I'm going to drill one. We do a little peck drilling, which means we go part of the way in, pull the bit out, breaks the chip free, a little further, pull it out, extend, and we'll go all the way through the piece. We want the hole completely through. The parallels are grabbing the edges of the piece, so as the drill bit goes through, it's not going to run into anything below there at all. So using a little bit of lubricant as we go down is a really good idea. It makes the cuts faster, easier, chip removal better, and makes my tools last much longer. Drilling is one of the least fun things to do because, as you can see how the chips grab the drill bit, when they decide to let go, they also like to fly. And since I can use my vacuum to pick up some of the trash around here, it doesn't pick up these spiral cuts very well. It'll jam it up, so I have to pick them all up by hand ahead of time. A little magnet on the stick helps pick up some of those. So I've got a group of pieces to drill holes in, and once they are drilled in, we'll go on to the next step. 1 down, 5 to go. You can see how the stop now allows me to push that piece right up against it, knowing that dead center for the first piece is the same dead center as for each additional piece. And a little fast forward here gets us through this operation pretty quickly. So now, without moving any pieces, I'm going to start doing the tapping. And I've installed a tap in the tap handle. And in the head of the mill, I've installed a follower that is spring-loaded. There's no pressure being applied, it's just a spring. What that does is keep the alignment of the tap perfectly vertical while I am tapping the hole by hand. There is an automatic tapping feature on the mill, but because I'm going through such a thick piece of steel with such a small tap, I've decided to do this by hand. As the tap proceeds down into the hole, you can see that I've lowered the tap follower. I'm going forward about 1/3 of a turn and then backing up. And the backing up breaks the chip free, so as you mill a piece, I should say tap a piece, it's important to break those chips as you go. The smaller the tap, the more this is absolutely necessary. Burying a tap in a piece and breaking it is a very difficult job to remove, if at all. So now, you may not be able to see it, but on the tap itself, I placed a black mark. So I'm tapping down to a certain distance, but not all the way through. This is what's called a plug tap. The first 6 threads on it are incomplete, simply to start. The idea is to go all the way through a piece, cutting threads, but I'm stopping short at that black mark. That means that when I screw in a bolt or other device, it's going to jam at the bottom of the piece and not pass freely all the way through, which is precisely what I want, because I want to lock it into the T-nut and tighten on the top. Now I'm putting, again, that tapping fluid on there just to simply to keep the tap in as good a shape as possible. Once that's all done, we're almost finished. We've got the shape, we've got the hole, but we now need to make the T shape by taking a certain amount of material off of each side so that it fits into that T slot. So I'm going to mill one side. I've made my measurements, again from that dead center location, which was set up and is being tracked with the digital readout. As you can see, I have a different cutter in here. This is the Niagara. It's a 1/2-inch cutter, a little smaller than the last one I used. I think it's cutting just a little bit better, and it's a very deep cut. So make one pass down that side, cutting against the rotation of the cutter. Pass over to the other side. Again, using the digital readout to set the exact width or distance from the dead center of the hole. And make the approaching cut coming down this side. Again, deep cut, slow feed, 1500 RPM rotational speed for the milling head. So once this cut is complete, if my measurements are right, we should be pretty close to being on the mark. So finish the cut. Let's go to a test. I'll remove my piece, check it to be sure that I'm close. Yeah, it's right where I expected it to be. So we'll take it out, go over to the slot, and it slides freely and loosely in there, which is precisely what I want. And with a little cleanup, that project is finished. Thanks for watching.